Hello, my name is Maria, and today we're going to be talking about the photoelectric effect. Okay, this is an atom, well, a model of one, and basically this is the nucleus in purple, and these are the electrons on the electrosphere. On the nucleus we have the protons and the neutrons, but today we're going to be talking about the electrons. Before we look into the electrons, let's take a look into light. Light, as we know, is a wave. This right here is the wavelength, and it's going to be playing a big part into what we're going to be studying today. So, scientists have been trying for so long to understand why some experiments have been disagreeing with classical physics. And then Max Planck decided that, hey guys, maybe light is quantized. And turns out it is. So basically, every energy that we see from light, every energy that we get, are multiples of a fundamental part. And that would be the photon. And this is the symbol for it. This is the symbol for a photon. And it carries energy, but not mass. But it does have momentum. The photon would be the smallest fundamental part you can get from light. And that's going to be playing also a big part in the photoelectric effect that we're going to be seeing right now. Light is an electromagnetic radiation. Turns out, if we receive this electromagnetic radiation into an atom, each photon is going to be able to take off from the atom one electron from the outer shell. For instance, let's say this one. But turns out there's a minimum frequency that you need to have in the light for the electron to be removed. The photon came over here and it gave enough energy to this particular electron, so the electron is going to be like, oh, I don't want to go on this boring routine anymore, and then the photon is like, oh hey, I can give you enough energy and you can leave. Turns out it had enough energy, and we're going to be taking a look into that real quickly, and it gave enough energy to the electron, so the electron is going to be able to just leave the atom. The first question would be, and how much energy really needs to come from the photon to actually remove an electron from the atom? So, this would be the equation that Max Planck, a German physicist, came out with, and this is taking into account for one photon. But if you have more, you can multiply this by n, which would be an integer. So let's take a look into this equation real quickly, it's very important. So this is the energy we're going to have for a photon. This is equals h, and h stands for Max Planck's actual constant. And it is h is equals to 6.626 times 10 to the negative 34. So you guys can see it's negative 34. Like the negative 34th power. It's a very, very, very small amount. That just shows us how we're talking about really, really tiny little things. So this is Planck's constant. Very, very little. And it's in joules times second. Okay, now you say there's an F here, you know? This F actually plays a big, big role. This F is the frequency of the wave. So the wave here, we're talking about the wavelength, which is just a distance between two peaks of a wave. But the frequency would be the amount of this wavelength that passes through 1 point per second. So some scientists have been asking themselves, what if we just instead a lot of light for an enormous amount of time? Will that light make the electron come out? No. What if the brightness is more, it's higher? No. Actually, what the electron really, really needs to get out of the atom is the frequency. Right here we have a nice graph so we have the frequency on the x-axis and the kinetic energy on the y-axis. And it shows that we need a threshold frequency right here. Every material, it's gonna be depending really on the metal or the material you're really dealing with. Every material has a specific threshold frequency. Okay, there's a minimum frequency that you can have in light to eject the electron from the atom. What if I have more frequency than that? Because, well, if you have less frequency than that, the electron is just not going to come off. Turns out, this is the equation that explains this relationship. You have the energy given from the photon, that's going to be equals the work function plus the kinetic energy. The work function is going to be standing for the minimum, the least amount of energy that electron is going to need to come out from the atom. So you guys can represent this work function, the H times the minimum frequency. The photon will be H times whatever frequency is coming from the electromagnetic radiation. And then you have the kinetic energy. Well, the kinetic energy, turns out, is going to be the remaining energy that he's going to get from the photon. And that's really going to affect whether, let's say you connect the metal plate that's going to be ejecting electrons to a circuit. And in the circuit you have a lamp. If this electron has more kinetic energy, this lamp is just going to be brighter. So it turns out the amount of kinetic energy you get is definitely going to influence if you have that connected in a circuit. What if we increase the amplitude of the wave? This right here is the same wave. The only thing I did was increasing the amplitude right here, from this to that. Okay, turns out if you increase the amplitude, let's remember, the only thing that matters is the frequency. If you increase the amplitude, all you're going to do is get more electrons ejected from the atom. That's not going to add any kinetic energy to the one electron we were trying to eject. So let's recap. What is a photoelectric effect? Okay, we had the atom. We're going to incite electromagnetic radiation into the atom. What's it going to affect? The electrons. More specifically, the outer level electrons at first, because if you go into deeper electrons, there's just going to be more energy. But energy, yes, the photons. We have light, and it can be particles or waves. Right now we're going to be talking about photons, and they have a specific energy, and it can be found depending on the frequency of the light of the oscillator. That's the frequency. Now if you have the minimum frequency, which is the threshold frequency that kicks off the kinetic energy, then you're going to have a work function. The work function is going to give you the necessary amount of energy to just, take an electron out of the atom. And if you take the electron out of the atom, he's going to be able to do whatever he wants, have fun in a current or whatever he decides to do. But if you give more frequency, what's that going to give to the electron? Well, more kinetic energy. All of the energy he gets from the photon is going to be giving, well, at first to the work function, and then the remaining is going to be giving to the kinetic energy. So let's talk about a really cool application of the photoelectric effect on our days. The automatic doors. Okay, right here is an example of a drawing of an automatic door. And right here you have a couple of photocells. These photocells are going to be emitting a beam of light. Turns out the photoelectric effect is going to be ejecting enough electrons for the system to emit a current. It's going to be connecting that to the door. And whenever you just interrupt this beam of light, the system will know and the doors will open. Well, another is a very important example nowadays is the solar panels. Okay, the solar panels, they get the electromagnetic radiation from the sun, and the photoelectric effect is going to inject enough electrons to create a current, thus transforming thermal energy into electrical energy. And that's very important nowadays for us. Okay, so this is a photoelectric effect, guys. Thank you very much for watching, and thank you so much for this opportunity. It's been a pleasure, and it was very nice to talk about something that I really appreciate and enjoy. It's just really interesting to learn how a photon can give enough energy if it has a minimum frequency to just, eject one electron from the atom. I mean, that's really nice to learn. And that's it, the photoelectric effect.